Today, you guys will notice we got Chapter 7, Systems of Matrices, PreCalc 7.1 notes. Okay, we're going to have 2 days of notes in this one, and the overview of what we're doing. Many applications of mathematics and science, engineering, business, and other areas involve the use of systems of equations or inequalities in 2 or more variables as models. We investigate several techniques commonly used to solve each system, and we investigate matrices which play a central role in several of these techniques. Now, 7.1 is solving system equations. 2 is matrix algebra. 7.3 is multivariate linear systems and row operations, so you'll be using your calculators for that. It's kind of a cool thing that your calculators did. I had a master's class of 2 semesters at the U. You had to do it with no calculator. All the stuff you did, all the manipulation was calculator free, so you will appreciate your calculator, trust me. Partial fractions, okay, that's kind of a fun thing, and systems of inequalities in 2 variables, and that'll be it. That's the section. That's the chapter. It's about 2 weeks. The information age made the use of matrices widespread because of their use in handling vast amounts of data. Matter of fact, they're called arrays in computer science, and you read the array and it just kind of presses it into your program, and your program, you have a array meter and be able to cover it and stuff. But we're going to be using matrices light. We're not going to be going crazy. And as I've got over here on that right side board, review solving systems. Hey, we've done this stuff before. Okay, so we're just reviewing system solving. We're going to talk about graphing, substitution, elimination. We're going to solve versus solution versus no solution, see what that looks like. Infinitely many solutions, okay? And we're going to get to the applications because we're going to get to both days of notes in today. Now, I'll be able to, for 7.1, hit by substitution, by graphing, linear combinations, and we'll do some applications. So let's get this bad boy going. A solution of a system of 2 equations and 2 variables is an ordered pair of real numbers that is the solution of each equation. If we solve the system of equations when we have found all of its solutions. So we've got it solved if we got them done. Okay, that's what's being asked. In our case, we're going to show work. On this first one, I'm going to talk about doing substitution as we go through. And part of substitution would be able to solve for a variable. I'm going to solve for y. It's the easiest variable to solve for. That's why I'm picking it. If you wanted to, you could solve for 2x, and solve for x as we go through. So I'm going to take that 2x minus y equal 10. I'm going to take the x on the other side, plus 10, and I'm going to take the opposite of everything. So right now, I know where I see y. I should probably be a little bit more careful. In the other equation, I'm just going to pop it in right there. And please keep in mind, I've got to use the other equation. I didn't manipulate, okay? I don't plug it back into itself because it won't work out the way I'd expect, okay? So now, what I've got this going, I got 3x plus 2 times y, and y is equal to 2x minus 10 is equal to 1, okay? At this point, I just combine like terms. Okay, I've got 7x equal 21 and x is 3. Okay, and just like we did before, okay, after I do that order of operations solving, I got x. I need to find y. It's a system. It's a coordinate pair. It's where my 2 lines in this case will cross. So I've got to take the other equation. So I already solved it. So I suppose I can just go and plop 3 in here. So 2 times 3 minus 10. 6 minus 10, so I get y is negative 4. So I have a solution. I got y equal negative 4, x equal 3. I can represent it that way. I can look at my solution as a coordinate pair, 3 and negative 4. Okay, so that's my answer right here as I go through. And what's it look like is when I graph my 2 lines, I've got it set. And I pre-graphed those because I was figuring that y'all are okay with linear graphing, and that's where we're off to. Go ahead, check that out and get your graph going on. And this gives me an opportunity to talk about solving systems by graphing, because right here I've got a system, my first system, my second, my system of the 2 graphs, and the place where they cross is the solution. So I have a pictorial solution and I have an algebraic solution here. And I'm just pulling up my calculator right now, so y'all can see what's going on there. I was going to be using it eventually here. I'll hide it back here. Okay, so as we're going here, we got this stuff going on. Are there questions about systems? I mean, this is review, and you go, oh yeah, I remember this. Okay, just plugging in the information. And we're going to be doing this plugging in thing quite a bit. Okay, now solving nonlinear systems of substitution. Well, here's the deal about this nonlinear solution. When I do this, I'm looking at finding the dimensions of a rectangular garden that has a perimeter of 100 feet and an area of 300 feet squared. Okay, so I'm imposing upon myself restrictions on my garden about what I do. Maybe I just got this fence laying around and I've got this area in my yard. I want to see if I can use the fence. Okay, find the dimensions, but when I do this, I got perimeter first. I'm going to go after that. Length plus width as I go through, and it's 2 times length plus width. And they tell me I got 100 feet. So I plug in 100 for perimeter. And I am going to kind of solve for length and width. I'm going to divide by 2, so I got 50. Now at this time, I have a choice. I can have it as L is equal to 50 minus W, or W is equal to 50 minus L. I don't care which one I do. I'm going to be honest, I'm going to substitute L, because L looks kind of funky in my solving, so I'm going to get rid of it. It kind of looks like a weird looking 6 or something. It could be some weird number for folks, so I'm just going to use W. So I got 50 minus W is equal to L. I could have totally set it up the other way. Now, as a system, I have to have 2 relationships, 2 unknowns. Okay, if I have 3 unknowns, I have to have 3 relationships, and so on. Okay, that's why there's a benefit to using matrices when we do this. So an area is length times width. And some of you are like, well, duh, Bloom. Okay, but as we go through this, I know the area is 300. So my area is 300. Okay, maybe perhaps we can write that 3 a little better. So my area is 300 is equal to L, which now I know is 50 minus W, times W. Okay. Well, gosh, this is looking like it's a quadratic. So I've got 300 is equal to 50W minus W squared. I'm going to get everything over to the left. W squared minus 50W plus 300 is equal to 0. Do you remember completing the square? That's what I'm going to go for. W has to have a leading coefficient of 1. If it doesn't, I have to divide it out. Okay. Then I go half of 50, which is 25. And I'm going to set it up a little bit better. Hopefully me resting my finger on the board won't be so much of an issue. Plus something is equal to negative 300. Okay. Plus something, whatever that something is. So half of 50 is 25. 25 squared is 625. So I'm putting in 625 on both sides. This ends up being W minus 25 squared is equal to plus or minus, excuse me, not plus or minus yet, I'm getting ahead of myself, 625 plus negative 300 is 325. So that's where I'm at. Okay, yeah?
What's the formula for like that middle value?
We're looking at the idea that I've got A, well, it's got to be 1. So if I really am looking at W squared plus, and I've got my B, bless you, W plus half of B squared, okay? But I got to keep in mind that I had a C on the other side, and I'm going to add my B over 2 squared. Okay, so that's pretty much the thing I'm coming up with as I'm finishing this up. This is B over 2 squared that I'm adding in there at the end. So I'm going to slide that over a little bit. Okay, and B can be negative, but remember when I square it, it's positive as I go through. So that's pretty much basic for my completing the square. Okay, now I'm at this point, I'm going to take the square root of both sides. So I got W minus 25 is equal to plus or minus the square root of 325. Okay, I'm going to add 25 to both sides. And that's my thing I'm looking, ooh, somebody can't write this other 5 in there very well. Plus or minus the square root of 325. So I take my calculator out, and I did this beforehand, and I've got W is my possibilities for W as I do this are 430.277, or excuse me, 43.028, or 6.972. Now, here's the thing about it. Those are my answers for W, but whatever I choose to be W, that's also my L. So in this case, I decided to go with my dimensions. I got W is equal to 43.028, and my length, and remember, all I did was put 43.028 into this equation up here and come out with my length, which was 6.972. So that's where 6.972 is coming from. And those are feet for both of them, okay, as I step through. So those are my dimensions they asked me to find as I step through. Keep in mind the purpose of doing this. 2 relationships, 2 unknowns. They gave me a relationship for area. They gave me a relationship for perimeter. That's how I was able to do perimeter equals 2 times length, you know, the quantity of length plus width, and area is equal to length and width, okay? Otherwise, I can't do this. I have to have 2 relationships, 2 unknowns to get it done. Moving on, maybe, we're also looking at, in example 2, we did not round the values found for X until we computed the values for Y. For the sake of accuracy, do not round intermediate results, okay? That's rounding error. I'm sure you've heard that over and over in science. You round once at the end, okay? Carry all decimals on your calculator computations in there, and then round the final answers all the time. Now in this next one, we're going to be solving a nonlinear system. Well, what is the purpose of this? We're really talking about the fact that we're looking at y is equal to x cubed minus 6x and y equals 3x. I want to know when they coincide, when they're equal. So we set it up a system. And so now I can substitute in for y 3x. So we're actually going to do it the other way around because it'll be easier to do the solve. I've got x cubed minus 6x is equal to 3x. Okay, so I got x cubed minus 3x minus 6x is equal to 0. Keep in mind that's 9x. So I've got x times, now I'm going to go a little slower, x squared minus 9. And x is equal to x minus 3 and x plus 3. Well, I've got this three-dimensional, I got 3 ways to work with zero product rule. I mean, one of them is 0 for the product to be 0. So either x is 0, or x is 3, or x is negative 3. Now, at this time, where do I get my y? I have 2 relationships I can plug it into. I don't care which one you do, I'm going to pick the easier one. If I've done it right, that'll work. Okay, so x is 3, I pop that in, my y is 9. So 3, 9 is one of my answers. And it should have been 0. I don't know why in the world I said that. We're going to take care of that. That one's x is 3. I have no idea why I did that, but plop 0 in, 0, and 0. That's one of my answers. Plop negative 3 in. Negative 3 times 3 is negative 9. So I've got negative 3 and negative 9. So I've got my 3 possible answers. I check out my calculator. I put the 2 relations in, y1 and y2. Now keep in mind, I just showed algebraically my system solve. You get points for that. If you just go, well, it's in the calculator, it's here. Yeah, you'll get your 2 points or 1.5 points, and the remainder will be taken away. Okay, but right here, negative 3, negative 9. Okay, up here, 3, 9, 0, 0. Those are my spots where my answers are. Okay, so I have it a visual with my calculator, and I can actually trace it. But if you're asked to solve, show your solution. Okay, as we're going through. Now, systems of equations graphically. Okay, this is what this equation looks looks like I want to put in the log of x and x squared minus 4x into my calculator. So if you would do that as well, that'd be pretty cool. Go ahead, pop those in. Okay, I kind of preset the calculator up there. I put the log of x, natural log I should say, of x. And remember, natural log of x is defined from 0 to infinity. Okay, so there's an asymptote at 0. Okay, and the other one's all good because I don't have any restrictions on the other one. I hit my graph as I go through, and the place where they cross is my solution. Okay, well, just like my little picture here, I've got a solution in 2 spots. Okay, so as we go stepping through, they say, hey, draw the graphs of the 2 equations in y 0, 10 to negative 5, 5 viewing window. I don't know if that's my viewing window, okay, but that's pretty much what I'm solving. Okay, so these 2 spots where these 2 graphs will intersect are my solution. Okay, questions about what I did? So I can do, intersection. I can trace that and come up with my 2 spots. Okay, so there you use a graph in part 1 to find the coordinates, the points of intersection. Got them. Those are my 2 points of intersection. I got x, y coordinates for each. For my 2 intersections, I just kind of did them the other way. This one's here. This one's over here. Those are my 2 intersections. Okay, I'm totally using my graph y1, y2 to get her done. Okay, now this next part is talking about our understanding for end behavior. Okay, as I talk about the log of x kind of goes up really slow. Okay, but it constantly increases. It goes from negative infinity to infinity for its range. Okay, and it increases really slow. All right. This one, this x squared, kind of increases faster as depicted by our graph, but it also goes to infinity. So because of my end behavior, I can surmise that, hey, these are the only 2 spots that these 2 graphs are going to cross. And that's what I'm talking about in this next section. Okay, the log of x, the natural log of this, is defined from x greater than 0 or from 0 to infinity. So all solutions must be positive. Okay, I shouldn't say all solutions. All values, domain values in are positive. Okay, so from 0 to infinity, that's where I'm worried about. Okay, so as x approaches infinity here on this one, and x approaches infinity on this one, because as this one goes, it goes in negative infinity, but I don't cross again there, and I'm not too concerned with that. I'm more concerned, and I don't know why I didn't show that I'm more concerned as x goes to infinity of the natural log of x. Well, that's going to go on infinity as well. Okay, and the issue that I have with this now is, why am I doing it? I want to make sure you recognize the 2 places they cross or will be the only 2 places they cross based on end behavior. Okay, I'm going to give you some time to get that down. Going on, I want you guys to have an opportunity to practice this. So y1, y2, just check them in. I got to set them up. Natural log of x, it's not 21n, it's 2 natural log of x and x squared minus 1. Okay, those are the 2 things I'm putting in. And I'm going to graph. Hopefully, maybe, if it allows me to. There we go. And as we come through, we notice that I didn't get the other one highlighted because I'm highlight challenged apparently today. There we go. Now we'll graph, and hopefully I'll come through. Now, I can kind of estimate what's going on, but if I do a trace, I'll be able to find it. But just because the trace found it, because remember, that's based on where they're crossing, okay? I'm going to put in, I think it's 1, 0, so I'm just going to pop it in. So here, I check out y equal 2 log of x when that's 1, and I'm going to check out y equal 1 squared minus 1. That's going to be 0, and incidentally, this is 0 as well because the natural log of 1 is 0, okay? That's the 0 power. So it's going to cross at 1, 0 as I go through, okay? And I've checked it with the calculator. I've actually further checked to make sure that that's the case algebraically. Show, hey, this is the point where they're crossing. And there isn't another spot. They just kind of kiss right at that spot, okay? And just to make sure, one of the things people are always wondering about, if I zoom, I can zoom in, maybe. I keep forgetting about that. And I can make a box, or I can box zoom. But if I pick where I want to zoom in, that area, just to make sure it doesn't cross funky, and I just got one of them, I got the top one or the bottom one, I can actually pick the area I'm going to zoom and hit enter. And it'll zoom into that area, and I'll be able to see a little bit more visual inclusive that that's where it's coming in contact with it. But I also proved that my thought of 1, 0 is there by plugging them in the way I did, okay? Now, that's solving nonlinear systems graphically. Let's talk about elimination methods. Okay, to solve by elimination, rewrite the two equations as two equivalent equations so that one of the variables has opposite coefficients. Okay, this has been known as linear combinations from your Algebra 2 text. So as I'm looking at my thing, I apparently eliminated my equation, my original equation. So I'm just going to hop those up real quick. Oh, this gets right here. So using the elimination method, I should be working with 2x plus 3y. And you would have been given this. It's not anything you would just come up with. Sorry, I just deleted that when I was prepping my stuff earlier. And part of elimination is I look to see which variable I want to get rid of. Okay, I'm going to try to get rid of my y's. Okay, so, or my x's. I don't care which one. And since I've got that negative, I'm just going to multiply the bottom equation all the way across by 2, the top equation all the way across by 3. Because when I'm done with that, and this whole thing by 3, I'm going to do this whole thing by 2. So this will become 6x plus 9y equal 15. The bottom will become negative 6x plus 10y equal 42. Okay, in doing this multiplication, I'm able to get rid of one of my variables. I could have done the another multiplication. I can multiply the top by negative 5 and the bottom by 3, and I would have gotten rid of my y's after adding. So at this point, I'm just going to add. 6's are 0. I got 19y equal 57. Y is equal to 3 after I divide. Okay, and now to get my value for x, let's pop it in. 2x plus 3 times 3 equals 5. 2x plus 9 is equal to 5. Subtract my 9, 2x is equal to negative 4. And x is negative 2. And again, my answer, negative 2, 3, okay, is where I'm going. It's for my solution. That's all I'm doing. And this is review. Are there any questions about what we're doing as we're stepping through? Feeling okay with these? Okay, the other part of this is finding out what it looks like algebra-wise of no solution and graphically no solution. Graphically no solution, you have two parallel lines, okay? Algebra-wise, if you are able to do the multiplication, if you just go through and we do the setup, I'm just going to take the top and multiply the top by negative 2. That way I only have to multiply 1, okay? I'm going to get rid of my x's here. So if I multiply the top by negative 2 in this example 5, I got negative 2 plus 6y equal 4. And the bottom is just negative 2x. It's 2x minus 6y equal 4. Well, when I do my addition, or my setup here, it doesn't make sense, okay? So I'm looking at this is 0, this is 0, and this is equal to 8. So I get my final is 0 is equal to 8, okay? This doesn't make sense at all. There's no solution to this relationship, okay? And I want to double check, you know, maybe I screwed up. But when I do this, there's just no solution. Now, why is that? If I look at this, the lines are parallel, they'll never cross. Now I can show that by just solving for y and showing that the slopes are the same, okay? So lines are parallel, will not cross. And the area, the spot where they cross is the solution, the point of intersection. That's why this is no solution, it's parallel lines, okay? And I could go step through and show that the two equations have equivalent slopes to show that they're parallel, okay? Now, stepping on, graphing the equations on your graphing calculator in the same window can help you determine the number of solutions in a system of two linear equations and two variables. Now, if they cross, you got one solution. If they're parallel, you got no solution. If they lie on top of each other, they coincide, you got infinitely many solutions, because think about what that's saying. If I have one equation and the other one's right on top of it, they intersect along the entire length of the equation. So there's infinitely many solutions. If they are parallel, they don't cross, so there's no solution. Okay, but what's an infinitely many solution look like as we go through? Well, here, if I multiply the top by 3, I will have met the bottom. So I've got 12x minus 15y equals 6, bless you. Negative 12x plus 15y is equal to negative 6. 0 is equal to 0. Now, remember I had 0 before, but it didn't make sense because 0 equaled some other weird number that it wasn't true. In this case, it is true. So 0 equals 0, I've got infinitely many solutions. So that's what I've got going. The lines coincide, that means they're the same. Yeah.
So they would be like stacked on.
They're right on top of each other. It just happened to be a multiple of the same line. Okay, that's all that is. But algebraically, you get 0 equals 0 for infinitely many. For no solution, you get 0 equals some other number. If it's 0, 0, no solution. I mean, infinitely many solutions. If it's 0 equals some other number, it's no solution. Now, as we do applications on these today, I've got L1, L2, L3. Those are the areas I plugged this into my calculator, okay, online, okay. But before I get there, I suppose I should talk about it. Table 7.1 shows the personal consumption expenditures in billions of dollars for dentists and health insurance in the United States for several years, okay. This source is the Department of Commerce Bureau of Economic Analysis, by the way, where we got this. And I just got notes in here because I had all those other equations in Y1, Y2, Y3, and Y4. I'm going to put my linear regression for the two sets in Y5 and Y6, okay? So what I'm going to do is in L1, I'm going to enter this information. In L2, I'm going to enter this information. In L3, I'm going to enter this information. And then I'm going to run an analysis with L1 being my X, L1, L2, and L1, L3. And I'm going to find where they cross, okay? And keep in mind, I have a picture of this right here, where they cross. It's actually back behind the y-axis, okay? So it happened sometime before 2000. 2001, okay? And I'm just entering in 1, 2, 3, 4, 5, 6, 7, choosing to do go on. So what I've got here in my stat edit, maybe if I can get there, is those pieces of information, okay? Now, once I get those entered, I'm just running a linear regression on those values. And I'm going to place those equations in Y5 and Y6. Again, on my calculator, they're already used for this notes. So that's why I'm going to do it that way. No, I forgot where these are. Oh, they're in stat. There they are. So I'm going to do linear regression in number 4. Okay, I've got L1, second L1, and still not working. No, it's not helping me. Oh, because I'm an idiot. Okay, let's go back to linear regression under stat. Calc. And I got number 4. Okay, second L1, thank you. Second L3 is what I want to do. L2, excuse me. Okay, I'm going to save this first one in Y5. Just going to double check to make sure that's where I have it. Yep. Imagination of that is you're going to find your linear regression, and it's going to be lin reg, I think, in your calculator. I think there's a left parenthesis, and then you're going to do your L1, comma, L2, comma, and then I'm going to store this, so you put it in your Y whatever, and you find that on your function, and you can close it up, okay? But it'll be in that line as we go through. And then when we make the changes, it'll be L1, L3, Y6, okay, if you have one of the older calculators. I'm not going to do anything with the frequency list. Where I want to store it, I'm going to go under vars. I want to go yvars, function, and I'm going to go to Y5 because that's where I said I was going to store this. Okay, and then I'm going to hit calculate. Okay, and now it's got all my stuff in there. I can totally write this down. It also is in my calculator right now, so I'll be able to graph it in a sec, but I got to do the second one. So I go back to stat, I go over to calc, I hit 4, and I'm going to do my second one. My L1 is my X values, L2 is my Y values, and I'm going to do L3, second L3. Okay, I said that I was going to store that in Y6 so I can compare the two variables. Y variable, I'm going to go down to 6. I could also, since I already know I'm going to 6, maybe if I can get enter, it's Y6 is across from 6. I can go there, and then I can go calculate. And now I've got those two equations, my Y5 and Y6. I can arrow down, unselect Y3 and Y4, check my window for my values. Okay, my window, as I'm looking through my numbers here, I'm going to go back -5. I might go back -10. So -10. I'm going to go up to 10. For my X values, left and right, my up and down values look like I've got from, I could probably get away with 50 to 200. Okay, for my Y values, I'm going to go to 40. And I'm going to go up to 200, not 4, but 40. Up to 200. And I did that from my table. I just kind of put them in there. And now I can hit graph, maybe. That place where they cross, I can find that on my graph. And by doing intersect.
How to get the R in there?
That is my calculation stuff. I can show you right after we're done with the video, but that's just to show, you know, how good is my regression analysis model. Okay, so that's what I'm doing. I'm going to get back there. I'm going to go hit trace, second calc. I want to go intersect 5. I want to do the intersection of the two. I'm going to just get close to my intersection. Hit enter. And then hit enter again. And then finally, and they say like -2.5, right? That's where it is on my X. I don't care, you know, Y it goes up at 49, okay? But -2.5, if I go from 2000 and add -2.5 to it, it's sometimes 97. It's just after July, Okay, so as I'm going through this, they ask, use the models, estimate when the U.S. personal consumption expenditure for dentists was the same as that for health insurance and the corresponding amounts, and it was sometimes in 1997. Okay, they didn't tell me when this data was taken, so that's why I said sometimes in 97. I don't know if it was in January, July, or just randomly collected during the month. So that's why I'm saying it vaguely like that. Okay, so that's a way that we can use this model to determine previous information, okay, but assuming it continues on. And again, anytime we have a model, the further we go out, the worse our estimate can become. So we have to like reassess every few years when we have a model. We got one last thing. I'm not going to pretend I'm a business major, but we do work with supplies and demand curves on this. And your suppliers will increase production X if they can get a higher price P for their products. So as one variable increases, the other also increases. Consumers, okay, your consumers, demand X for a product will decrease as the price P goes up. Okay, so as one variable increases, the other decreases. And this is unique as far as the general public is concerned, but I remember, and it's a sad thing that I can remember back this far, but when beta recorders came out, or VHS recorders, they were like $400 and $500 and $600 when they first came out. And back in the day, you got to keep in mind, a calculator that we would get, jeans would be like 10, 15 bucks. That was astronomical, the amount of money that they were. But when there is a low quantity, price is high. You know, demand's high. And that supply and demand curve where they meet is the sweet spot where manufacturers are making enough to make a profit and consumers are happy about the amount of money they're paying for that product. Okay. Now, you guys may have witnessed VCRs being 20 bucks. I got a VCR DVD player that was $35. If I had first came out, DVDs were crazy high too, you know, when they first came out, but the market was so saturated, they were just making units and trying to get rid of them. So this supply and demand curve is a sweet spot for, you know, manufacturing, consumerism, so that way we can get it over. I think the company that's got the best supply demand curve setup is Harley Davidson. Okay, they have a nice price point. People are willing to wait months for special bikes from them, and they're willing to pay out the money. That I think has the best sweet spot ever. But you know, I digress about that. Let's talk about what we're looking at for this determination of supply and demand. Determine the equilibrium price, the sweet spot. Okay, Nybach Manufacturing has determined that production and price of a new tennis shoe should be geared to the equilibrium point for these two systems. Now, this is based on information that's collected. Now, keep in mind, the sweet spot, where do they meet? One's demand, the other supply, I got a sweet spot. Well, this is a system of equation. I set them equal and I solve. Okay, so I get this thing going, and I got 125 equals 25x, and x equals 5. I plop that in to this. Now remember, I could plop it in, but this is my demand, and I'm looking for my price. P for my price, and it should work in both situations, is 135. Even if I picked the other equation, if I decided to pick the other equation, because this is where they are equal, this should also be 135. If it is not, I've made a mistake in my evaluation. But what's this mean? 5 million pairs of shoes will be produced. Where did 5 million come from? We had 5. Well, it was in millions of shoes. Okay. Each pair will cost about $135. Okay. That's how they set the price points. Now, they have test markets that they do this in. We did a test market thing in the beginning, and they will find out how many units are sold at a certain price, and based on the units sold at certain prices, and they change those variables throughout to determine the sweet spot for price to maximize profit. Okay, but it really hedges around the supply-demand curve stuff. Okay, that's notes for the 2 days. You have to assignment tonight, and tomorrow's online learning, the online learning on Wednesday is just completing the 7-1 day 2 assignment. That's all you're doing. Okay, it wasn't supposed to be heavy duty, it's just doing an assignment. Okay, so the day 2 assignment, I got them both up here and I got them both up there.